CloudRun is a fully managed serverless platform that allows you to run containerized applications without the burden of managing the underlying infrastructure. As a serverless platform, CloudRun abstracts away all infrastructure concerns, allowing developers to focus entirely on their application code and business logic. CloudRun eliminates this complexity by providing a fully managed environment where Google handles all infrastructure operations automatically. This module will explore the core mechanics of CloudRun, focusing on three fundamental runtime characteristics that define how applications operate in this serverless environment. The first core mechanic is container lifecycle management. CloudRun automatically handles the creation, scaling, and termination of container instances based on incoming traffic demands. The second core mechanic is automatic scaling. CloudRun dynamically adjusts the number of container instances from 0 to thousands based on incoming request volume, ensuring optimal performance and cost efficiency. The third core mechanic is intelligent request handling. CloudRun manages how incoming requests are distributed across container instances, with configurable concurrency limits and sophisticated load balancing algorithms. These three core mechanics work together seamlessly to provide a robust serverless computing environment. We will use step-by-step animations and detailed graphs to explore each of these concepts in depth throughout this module. The container lifecycle in CloudRun encompasses three critical stages that determine how your applications are deployed, managed, and terminated. These three stages form a continuous cycle that CloudRun manages automatically, ensuring optimal resource utilization and application performance. Let's examine the startup phase in detail. This is where CloudRun transforms your container image into a running application instance. During startup, CloudRun first materializes the container image. This process involves extracting and preparing all the files, libraries, and dependencies your application needs to run. Once the root file system is created, CloudRun executes the entry point program specified in your container configuration. This is where your application code begins running and becomes ready to handle requests. The scaling phase represents CloudRun's dynamic response to traffic demands. This automated process ensures your application can handle varying loads efficiently. CloudRun continuously monitors incoming traffic and automatically creates or destroys container instances as needed. This ensures optimal resource allocation without manual intervention. When traffic decreases, CloudRun automatically scales down by terminating unnecessary instances, optimizing costs while maintaining service availability. The shutdown phase occurs when containers are no longer needed or when new revisions are deployed. CloudRun manages this process gracefully to minimize service disruption. During shutdown, CloudRun follows a graceful termination process. It stops accepting new requests, allows current requests to complete, and then cleanly terminates the container instance. CloudRun's comprehensive lifecycle management ensures that your containerized applications run efficiently and reliably throughout their entire operational lifespan. This automated lifecycle management is fundamental to CloudRun's serverless architecture, providing developers with a robust platform that handles infrastructure concerns transparently. CloudRun implements intelligent autoscaling that automatically adjusts your application's capacity based on incoming traffic demands. The platform continuously monitors incoming requests and dynamically scales container instances up or down to maintain optimal performance and responsiveness. CloudRun's scaling capability ranges from 0 instances during periods of no traffic to thousands of instances during peak demand, providing exceptional flexibility. The autoscaling trigger is based on CPU utilization during request processing. CloudRun scales out when CPU utilization exceeds 60%. This intelligent autoscaling mechanism ensures cost efficiency by only running the resources you need while maintaining application responsiveness during traffic spikes. CloudRun implements sophisticated resource management through CPU throttling and handles service initialization through cold starts. Understanding these mechanisms is crucial for optimizing application performance. CPU throttling is CloudRun's method of conserving resources when containers are not actively processing requests. When a container becomes idle, CloudRun automatically throttles its CPU allocation. When the container becomes idle and no requests are being processed, CloudRun throttles the CPU to reduce resource consumption and costs. However, when a new request arrives, CloudRun instantly unthrottles the CPU, restoring full processing power without delay. This ensures optimal performance when needed. Now let's examine cold starts, which occur when CloudRun needs to scale a service from 0 instances to handle incoming traffic. A cold start happens when your service has 0 running instances and a request arrives. CloudRun must create a new container instance, which introduces additional latency. Cold starts introduce additional latency because CloudRun must initialize the container environment, load your application code, and prepare the runtime before processing the first request. To mitigate cold starts, CloudRun provides the min instances configuration. This ensures that a specified number of container instances remain warm and ready to handle requests immediately. By setting min instances, you trade off cost efficiency for performance consistency. The warm instances consume resources continuously, but provide immediate response to incoming requests, eliminating cold start delays. Understanding CPU throttling and cold starts enables you to make informed decisions about resource allocation and performance optimization in your CloudRun deployments. CloudRun's concurrency feature allows multiple requests to be processed simultaneously within a single container instance, providing efficient resource utilization and improved performance. Concurrency refers to the ability of a single container instance to handle multiple requests simultaneously, rather than processing them one at a time sequentially. CloudRun provides flexible concurrency configuration. The default concurrency limit is 80 requests per container instance, but this can be adjusted anywhere from 1 to 1,000 based on your application's requirements. The concurrency setting directly impacts resource allocation. Lower concurrency values require more container instances to handle the same traffic volume, while higher concurrency allows fewer instances to process more requests simultaneously. Understanding concurrency is essential for optimizing both resource allocation and minimizing latency. Higher concurrency improves resource utilization, but may impact per-request performance, while lower concurrency provides more predictable performance but requires additional instances for high-traffic scenarios. CloudRun uses a revision-based deployment model that ensures zero downtime updates and provides precise control over application versions. Every update to a CloudRun service creates a new revision. Each revision represents a specific version of your deployed service with its own configuration and code. When you deploy a new revision, CloudRun implements a zero downtime deployment strategy. The system starts new instances of the updated revision while keeping the current instances running. CloudRun starts enough instances of the new revision and waits for them to be ready before directing any traffic to them. This ensures your service remains available throughout the deployment process. CloudRun services are monitored by revision. Each revision maintains its own metrics, logs, and resource allocation. You can view the status and traffic distribution across all revisions. Inactive revisions can consume resources and incur costs, especially when minimum instances are configured. Unlike active revisions that scale to zero, inactive revisions with minimum instance settings continue to consume resources even when receiving no traffic. To optimize costs, regularly review and clean up inactive revisions, especially those with minimum instance configurations. This prevents unnecessary resource consumption and reduces your CloudRun expenses. While CloudRun provides significant advantages for serverless computing, understanding its trade-offs and potential pitfalls is crucial for making informed architectural decisions. The first major consideration is cold starts, which occur when CloudRun scales from 0 instances. This introduces latency as new containers must be initialized before handling requests. CPU throttling presents another significant challenge. When containers are idle, CloudRun throttles CPU resources, which can severely impact background tasks and scheduled operations. Resource overutilization or underutilization creates significant problems. Overallocation wastes money on unused resources, while underallocation degrades performance and user experience. Finally, CloudRun scaling behavior is less configurable compared to Kubernetes horizontal pod autoscaling. This limitation reduces flexibility in fine-tuning scaling policies for specific application requirements. Understanding these trade-offs enables architects to make informed decisions about when Cloud Run is appropriate and how to mitigate potential issues through proper configuration and monitoring. In technical interviews, understanding Cloud Run's auto-scaling mechanics is crucial. Let's explore a common interview question and how to answer it effectively. A frequently asked interview question is, how does Cloud Run handle autoscaling, and what are potential pitfalls? This question tests your understanding of serverless architecture and operational considerations. The answer has three key components: understanding the scaling triggers, identifying potential pitfalls, and knowing mitigation strategies. Let's break this down systematically. Cloud Run scales automatically based on two primary triggers: incoming requests and CPU utilization. When CPU utilization exceeds 60% during request processing, Cloud Run scales out by creating additional container instances. Now let's examine the most significant pitfall: cold starts. This occurs when Cloud Run scales from 0 instances, causing increased latency for the first requests. Cold starts introduce latency because Cloud Run must initialize a new container instance from scratch. This includes downloading the container image, starting the runtime, and executing your application's startup code. The solution to mitigate cold starts is configuring minimum instances. This keeps a specified number of container instances warm and ready to handle requests immediately. By setting minimum instances, you ensure that a specified number of containers remain active and warm. This eliminates cold start latency for the majority of requests, improving user experience at the cost of increased resource consumption. Understanding these trade-offs is crucial for interview success. You must balance performance requirements against cost considerations, demonstrating your grasp of operational decision-making in serverless architectures. In your interview response, emphasize that minimum instances provide performance benefits through reduced latency and consistent response times, but require careful consideration of cost implications and resource optimization strategies. Remember to conclude your answer by demonstrating practical knowledge. Mention that the optimal configuration depends on traffic patterns, budget constraints, and performance requirements. This shows you understand real-world application of Cloud Run's autoscaling mechanics.